אחרונה ובכיתי. לא, לא רוצה שאני אחרונה, כמה קומות מתחת ובכיתי. כן, וזה... שובר אותי. אני באמת מחזיק, אני עושה משפט. לא, אני סתם לא יושב בשיר. אז אפילו I didn't know someone else to play. Yeah, I know it. שלי תנוג מה אפשר לדבר, כאילו, אוקיי, נכון, מעולה. איזה כיף. מעולה. מה שלומך? לא. אני עושה שני קורסים פה, שני קורסים במדעי המחשב. שם אני עושה עיבוד שפה טבעית. יש אלגוריתמים שני. מי המנהל? כאילו אמרת עצמו יותר כיף לקרוא בבית. לא, השיעורים עצמם קשה לעקוב אחרי המחר. להקשיב. אז אני מעדיף. אני מחפש עכשיו ספר. אני לומד טוב יותר מאשר מספר. היום אני כבר לומר כמה מילים על ואני עכשיו אשלים סיכומים. חשיבתי. חולק אותיים חור בשיניים What? I would be like 30. What is the... I need lots of chocolate to make sense of it. Or is like the 70? Cavity is not too big for... You know, when you put this thing, dental cement. I think after that כמה מילים לגבי המבחן? about the exam. The exam will have two parts. It seems so there is no date that is accepted by everybody. No, I think we will. I think people. I mean, at least what I did, I just mentioned all the things that I wanted to be, but not things that I cannot do. So I think we should ask it differently. Not what is the most convenient for you, but what dates are impossible, and then we can make a better decision. Okay, I know about me and about some other guy that is not here today, that most of the days we can do the exam in. When you can do it. כשמשלבים את הלו"ז שלי שלו ושל גיל, אז נשאר בערך 3-4 ימים הראשונים במספר בחינות. כאילו, אנחנו תכננו את מספר בחינות שלנו מראש. But the date was the 4th. I mean, they changed it after 2 days. She told me that the date was 4th of February, and she told me that, and the day after I looked at it, and they changed it to the 1st. So it was not like that. They changed it like 2 days before we started talking about it. When I wrote this thing on Facebook was 1 day after they changed it. So it wasn't like this. They changed it because Yoram told them that it's going to be somewhere else.
No, but the dates were actually, it was after the signature started. Everything is like not the right order.
אני לא... אוקיי.
But anyway,
לגבי העדנים הראשונים...
but you don't have any. There's almost...
אני אשאל אותו איפה שינוי...
There's almost a month that you can do it. There's no single day that you can do in this whole month. It takes 20 days or something.
Yeah, because we have the next, we have only 2 exams, and the second one is on the 4th of March, so we are very, very flexible.
No, but
כאילו, אוקיי, לפי המודל נראה שאין צריך, העניין הוא...
כן, בגלל זה אמרתי, אני חושבת שמה שצריך לעשות זה מה אי אפשר בכלל, לא...
לא שואלים את השאלה.
לא לבטל, לשאול אחד אחד.
זה לא חדש תשובות, בגלל שמי שלא מצביע בפתח מסוים, הוא לא ימצא לך אותו. כאילו...
כן, אבל אז מילי מחליטה לשנות.
כן, אבל הדיון הזה, מה שהיה לפני הוא לא רלוונטי, כי הוא לא היה כאן, ושימו את זה בשנים
מה שהיה לפני שהוא כן רלוונטי, זה מה שצריך להישאר.
שישימו את זה
זה בעיה, אבל זה נכון.
זה לא חייב להיות אמיתי,
אפשר לדבר על זה שהיא שינתה אחרי שקבענו ביטול הקטנים ושל חדשים, אבל לקבוע את האחר זה בלתי זה.
סבבה, גם השמות של הרביעית הרבה יותר טוב מהראשון, זה 3 ימים.
זה לא הגיוני שמישהו יכול מישהו ואחד.
I would like to start. I heard some of the discussion. I think the situation is as follows. I'm not sure, but I think any change in principle in an exam requires agreement of everyone. Now, of course, it's much better. This is a small class, and it's much better if somehow it's possible to reach an agreement. But what might happen, I will need to discuss this with Millie, is that we will need to revert to the original date that was published in the Gideon, because even a change from that requires agreement of everyone. Okay, anyway, we have, there's still time, and hopefully it will be possible to do something which is good for everyone, or almost everyone. Okay, so we discussed Fisher information last week, and its relevance to discrimination and to estimation problems, estimation of fine estimation or discrimination of fine differences. And what I want to do today is to discuss how this concept can be used to think about the ability of a population of neurons to encode a variable, continuous variable. So we will start by discussing a single neuron, and our model of neural variability, as I mentioned already last week, is that the neuron is Poisson. Now you discussed this with Meta, so I will do it relatively briefly. I will not do the derivations, but I do want to go over the assumptions and the results. So if we think about a single Poisson neuron or a single Poisson process, the observation is the number of spikes, which I will denote by n. P of n is therefore e to the minus lambda. I use this kind of lambda to the n divided by n factorial, where now lambda might depend on some parameter that we want to estimate. So lambda is the tuning curve. As you know, for a Poisson process, the mean of the Poisson process is lambda, and also the variance is equal to lambda. So if we just plot the distribution of n,
John, could you put on the mic?
oh yeah, thanks. And also, who is taking notes? Great. So if we plot the distribution of n, p of n, just in two limits, when lambda is small compared to 1, essentially we have a process where the probability of spikes is very low. To leading order, it's just no spikes, but that's not interesting. So we can take into account the probability to have one spike, but the probability to have two spikes is already negligible compared to that. So we have a process where essentially p of 1 is equal to lambda, p of 0 is equal to, I will put here approximately, p of 0 is equal approximately to 1 minus lambda, and it's what we call a Bernoulli process. So we have a large probability to have 0, and some small probability to have 1, and we can neglect in this limit the probability to have a larger number. When lambda is much larger than 1, then we can think about, in general, we can think about, that if we sum two Poisson processes with mean lambda, we get a Poisson process with mean 2 lambda. So we can, when lambda is very large, we can think about this number of spikes as a sum over many Poisson processes with a lower rate, and therefore we know from the central limit theorem that we should get something that looks like a normal distribution. But it's a bit weird because it's a discrete distribution, right? So what happens is that we have something that looks like a normal distribution, but it's discrete. So this would be lambda. Lambda itself might not even be an integer, but close to lambda will be the largest probability, and then we will have probabilities with an envelope that looks like a normal distribution. Okay, so this is just what is a Poisson process. Now going back to this, so now we have really a distribution that depends on the parameter theta, and we can calculate the Fisher information with respect to theta. And you did this with Netta. So J depends on theta, and I will not do the calculation again. And what you got is f prime of theta squared divided by f of theta. Okay? So what I do want to do is to look a little bit at this expression and see whether it makes sense. And the first thing that I want to check is the units. So we discussed at the end of the last lecture what should be the units of Fisher information.
1 over the square.
Yes, 1 over the square of the parameter. Now f is dimensionless because f is the mean of the number of spikes. So the number of spikes is a number. It doesn't have units, right? So we don't have to worry about f. F prime is a derivative with respect to theta, so it has dimensions of 1 over theta, and therefore all this thing has the correct dimension. Okay, so that's fine.
Can you repeat?
You said that theta is dimensional?
Yes, and then we take a derivative here with respect to theta, so that gives us dimensions of 1 over theta, and it's squared. So we have units of whatever units are of theta, we have here the units of 1 over theta squared. So this is one note. Another note is that if f prime of theta is equal to 0, then the Fisher information is 0. That makes sense. If we happen to be at a position of theta where slight changes in theta do not change the possibility to do not change this distribution, then we're in trouble. Then theta, based on the observation, we gain very little information about theta. Now, does that mean that we cannot do discrimination or estimation? So let's think about discrimination. Let's suppose that we're at this particular theta. At this particular theta, suppose that f of theta looks like this, and at this maybe like this, and at this point f prime of theta does not the rate of spikes does not depend on theta. Does that mean that we cannot do any discriminations around theta? Well, I claim that if this function is not completely symmetric, and I want to say discriminate between this theta and this theta, maybe I can gain the f here and f here are not exactly the same, right? So it's really to leading order when we do a very fine discrimination task that we're in trouble. This doesn't. The arguments that we presented last week don't tell us that we won't be able to do fine discrimination for large changes in theta. Okay? They only tell us that locally. It just means that the scaling, if you have delta plus minus delta theta, our ability to discriminate small delta theta will scale differently from what we calculated last week. Last week we calculated a certain scaling with delta theta with a dependence on j, something that goes like square root j of delta theta. If we happen to be at a position where the Fisher information is 0, there will be a different scaling with delta theta. It will go more fast to 0 when delta theta is small. And also estimation. In estimation, if we generate some estimator for general theta based on observation of the spikes, then if the stimulus happens to be equal exactly to this value, then to leading order, so in general we saw that the variance of an estimator must go like 1 over the Fisher information, right? But that's really an upper bound. So it will it will behave differently, but it doesn't mean that that we will not be able to do anything. Okay.
Isn't it a lower bound?
So the mean square error is at least as smaller than 1 over j.
It's larger than
It's at least as large as 1 over j.
and then it's at least as large
Yeah, so maybe actually, this means actually that for an unbiased estimator for that particular theta, I need to think about it. Actually, it seems a bit strange, this statement. The Fisher information is 0. Maybe it's true that if the estimator has to be unbiased, it cannot give us any. It essentially means that we cannot construct an unbiased estimator in this case. But I think that with a little bit of bias, we could get a much smaller mean square error. I need to think about it. It's a good question. While I was talking about it, I realized that there's something a bit puzzling here. So I will think about it and tell you later.
Identifiability problem here, because those different theta get the same parameters.
Well, that's not the. I think that's not the issue. I mean, you could also think about something that goes like this. I don't think that this is the issue. Okay. No, finally, I want to note one other thing, and this is that what happens if we take our tuning curve and scale it by some factor. So the mean number of spikes is multiplied by the same factor for all values of the parameter. What happens to the Fisher information? What happens to the Fisher information? It goes like alpha. It's proportional to alpha. Does this make sense? Suppose that we multiply by 2 the number of spikes. We can actually think about the Poisson process with a rate which is twice as large as 2 observations of Poisson processes with the original rate. So this means like that if we multiply by some factor alpha, we can think about it as alpha different observations. We know that at least when we have many observations, the mean square error of, let's say, maximum likelihood estimator goes like 1 over the number of observations. And we also know that in this limit, the Fisher information goes like the mean square error goes like 1 over the Fisher information. So in some sense, it has to go like this. Okay. Multiplying by alpha is like having alpha independent observations. The mean square error should reduce by a factor of alpha. So it makes sense.
You're not really adding a new observation.
Yeah, but we have more. So okay, why is it at all? Why is it true at all that the Fisher information improves when f is larger? It improves because, or when we multiply by alpha, because when we multiply by alpha, the mean, we wrote it here, the mean grows by a factor alpha, the variance grows by a factor alpha, but the standard deviation grows only like square root of alpha. So the standard deviation becomes smaller relative to the mean, right? So we have like less noise relative to our observation. That's basically the reason. Now, specifically for a Poisson process, again, let's think about alpha equals 2. If we have a Poisson process which on the average provides 5 spikes, now I multiply it by 2. Poisson process that on average generates 10 spikes. This is completely equivalent to generating 2 Poisson processes independently that have 5 spikes on average and just summing up their output. So in that sense, a Poisson process with rate 10 is equivalent to 2 independent Poisson processes with rate 5. And that's why I'm saying that increasing the mean number of spikes is like having more and more independent observations. Make sense?
Can you think about it as like making the different, making a different patterns more different?
In some sense, yes. If we think of a discrimination problem, the mean number of spikes that will be generated, or the number of spikes that will be generated in different values of theta will be more separated to each other relative to the variability. Anyway, I think it just occurred to me that I was using the term Poisson process, right? And I should say Poisson variable. We're discussing now a Poisson variable. And actually, Poisson process is what I want to discuss next, and maybe this will also make it more clear why I'm saying that a Poisson variable with a larger number of with a larger mean is like 2 separate observations of a variable with a smaller mean. So I want to discuss now the concept of a Poisson process. Oops. So a Poisson process is an example of what we call a point process. And a point process is a set of timings. So we imagine that there is some event, and in a given instantiation of so a point process is a random process, and in a given instantiation of a given instantiation of a process is just listing the times at which events occurred. So just telling you that an event occurred at time t1, t2, t3. We can think about these as the spikes of a neuron. If I tell you the timings of the spikes of the neurons, of a neuron, that's an instantiation of the point process that describes the statistics of the spiking of the neuron. So if we want to specify in general a general point process, we need to say what is the probability for any pattern of timings of the I will call it spikes because we're thinking about neurons. So for any pattern of any length of timings, specifying the distribution of this process is saying what is the probability for any pattern of the timings of these spikes. Okay, so this is a very general concept.
The events are different?
No, they're completely. All I care about. Well, we don't associate any feature to these events except for the timing. Okay, so again, this is a very general definition of a point process. It's a random process in which we specify the timings of some events. Now, a Poisson process is a very simple instantiation of this concept, and it's defined as follows. So in fact, I don't know how to define it completely directly. I need to define it as the limit of a certain process, or but using some limits. So the idea is that Poisson process has the following properties. It has the property that if I take a small interval between time t and t plus delta t, and I ask what is the probability that an event occurs within this interval, then in the limit in which delta t goes to 0, this probability approaches lambda delta t. Let me see if I use small lambda. Yeah, I use small lambda. Lambda delta t. So this is property 1. And the second property is that the events in any two non-overlapping intervals, and it's crucial that they're non-overlapping, so say T1, T2, and T1 prime, T2 prime, are independent. So these two properties define the concept of the Poisson process. And in particular, it means, using property 2, that if we take if you think about a long time interval, we can divide it into very, very small intervals with infinitesimal duration. In each one of them, the probability to get a spike essentially becomes, because it's small, it becomes just this. The probability to have 2 spikes in each one of these intervals can be neglected. And it's independent in any interval. So it's really a process that is generating spikes with a certain rate. And the fact that a spike has been generated at a given time tells us nothing about the probability to generate a spike at any other time. That's the way to think about it. Okay, so
The lambda here is the same as the
no, I deliberately used a different small lambda here and large lambda here because the lambda here is dimensionless, right? It's the mean of a number of spikes. The lambda here has dimensions of 1 over time. So this is really the rate at which spikes are occurring, right? Okay, what else do I want to say? If we take an interval if we take a time interval delta t and we count the number of spikes that occur within this interval, what is the mean? What will be the mean? Did you say something? No? Lambda delta t. How do I know? I divide this interval delta t into small infinitesimal intervals. I know what is the mean number of spikes in each one of them. It's just lambda delta t, where this is this the infinitesimal delta t. And the mean of the sum is the sum number of spikes. It's the sum of the means. So if it's not clear to you, think about it more carefully. I will not do it very precisely here. And we could also ask what is the variance of n. And again, the way to it's easy to calculate it, because what you need to do. So the way you do it is you take your interval delta t and you divide it into these infinitesimal time intervals Greek delta t, and in every one of them this becomes a Bernoulli process with probability lambda delta t for a spike and probability 1 minus lambda delta t for no spike. You can calculate what is the mean of the number of spikes in each one of these intervals, and this is how you do this. You can also calculate the variance of the number of spikes in each one of these intervals, and the variances simply add up because the number of spikes in each one of these small intervals is independent. That's due to this property. So if you do all this, what you find, not surprisingly, that the variance 2 is proportional to delta t, and it's actually also equal to lambda delta t. Okay? So at any time interval, the mean number of spikes is lambda delta t, the variance of the number of spikes is lambda delta t, and in fact, I will not prove it here, but n is distributed as a Poisson variable with mean lambda delta t. Okay? Okay, so now that we defined this concept, we can think about it as representing the spiking activity of a neuron. So imagine that you have a neuron that fires Poisson spikes with rate small lambda, and lambda depends on some parameter, theta, and we observe the number of spikes that the neuron has emitted within an interval delta t. Okay, so let me write all this. Lambda depends on some parameter theta. And we observe number of spikes in interval delta t. We can ask what is the Fisher information available within this observation of the number of spikes about the parameter theta. And we don't need to do anything almost. We just need to plug. We know that this number of spikes is distributed as a Poisson variable with a mean lambda, which is equal to lambda delta t. So we just need to plug this in the expression that we wrote a few 15 minutes ago, 20 minutes ago. So what do we get? We get so let me just see how I wrote it here. So let's imagine that lambda is now some function of theta, and in some sense this is not good notation because I used f previously for the big lambda. Okay, so this f has different units than the f that I had before, but I just want to stick with the way that it's in my notes. So we now need to take f multiplied by lambda delta t and plug it as the previous f. Now we have the f prime squared divided by f. So what will change relative to the expression that we had before? In the numerator we have a delta t, which is squared. Right? Do you remember the expression that we had before? So in the numerator we had f prime squared. So now f is replaced by f delta t. So there's a delta t squared. In the denominator we have 1 delta t. So overall we get f prime squared divided by f multiplied by delta t. So the Fisher information is proportional to the length, the duration of the observation interval. Longer the observation of the duration interval, we have a better ability to estimate or to discriminate, and this makes sense. And now, within the context of the definition of the Poisson process, it's very clear, something that was not clear to you, I think, before, that a long time interval can really be thought of as a set of independent observations over shorter time intervals. Right? The number of spikes over a long interval, we can think about it as the sum of the number of spikes over a shorter interval, and that's why I said that in the limit where you have a long, here we think about it as a long observation interval, it's like a set of many independent intervals, and in that case we expect that we have more and more observations. Our ability to infer theta will be improved, and moreover, we understand now that when delta t becomes very large, the Kramer-Rao bound will become saturated. Okay. What did I want to say also?
I think what bothered me with this is just that there's no actual new information.
But there is. If I count the number of spikes within 1 second, and instead I now decide to count the number of spikes in 2 seconds, I do have new information. Why is this new information?
No, that's okay. Doing that, but I understood that multiplying by alpha is just taking these three, and just taking them again, looking at them as
No. It's not the same ones. It's like 2 independent observations.
But
when you multiply by alpha.
Multiplying by alpha, I used my intuition that I can think about it as the result of 2 independent Poisson processes with independent Poisson processes without the alpha. So if alpha is 2, say.
So if you just multiply.
So again, if
It's not
if I have a Poisson process that on average generates 10 spikes, and I now look at a Poisson process that generates 20 spikes on average, I can think about this one as the sum of 2 Poisson processes that generates 10 spikes. Which means that I'm summing up the result of 2 independent observations with the same mean. And that's why this one I multiplied the mean, but it's like summing up the observations of 2 independent Poisson processes, variables.
Like what I understood is that it's not like new observations, just emphasizes the differences.
That's also true. But it's also true.
New because you're looking at the same one twice. It's not like looking at 2.
Same one. The question is, what do we mean by same? It's the same distribution, but it's like 2 different instantiation of the distribution, which means that if we observe a Poisson variable twice, we do get more information about. if you
Like you're looking at the same exact observation.
look, if you flip a coin and you flip it once and you still know very little about the probability for the coin to fall on one side versus the other. Let's suppose that you're not sure that it's balanced. Okay, if you flip it once, if you flip it 100 times, you can already infer much better what is the probability of this coin to fall on one side versus the other. And if you multiply it 1,000 times, you'll be able to estimate that even better.
Yeah, that's fine.
Okay.
Multiplying that alpha is not like...
Alpha is just multiplying the mean.
Like
So
tossing the coin twice and then just...
yeah, so I'm saying that multiplying a Poisson variable, multiplying its mean by 2 is like, and looking what is the distribution, it's just like the distribution of two independent Poisson processes without the factor of 2. And in that sense, it's equivalent to having two observations of a Poisson variable. Okay. So again, so going back to the discussion of Poisson process, the fact that J is proportional to delta T, we can think about it as a result, a direct result of the fact that if we take the number of spikes, that J of delta T is like the observation. If I have a time interval delta T, I could split it up into two intervals of length delta T over 2, and I'm observing the spikes over each one of them. They're independent, so the Fisher information adds up. So J of delta T is equal to J of delta T over 2 plus J of delta T over 2. And that means that J has to be proportional to J to delta T. Now, actually, there's a subtle question here, which at some point you might think about, which is why am I, suppose that we're looking at a neuron, it's a Poisson neuron, and we're looking at its spikes. Why am I only counting the number of spikes? In principle, at a particular observation of the spike train that the neuron has generated, I can see what are the specific times in which the neuron is spiked. So what I calculated here is the Fisher information just in the total number of spikes, which is like throwing away the timing. We take a time interval delta T, and I just tell you the neuron has emitted 8 spikes or 7 spikes. I don't tell you at all at what times, specific times, these spikes were emitted. Maybe if I would tell you what are the times at which the spikes were emitted, you would be able to use this information to gain additional inference, to improve your ability to inference the parameter. So what do you think? Is that true or not?
Probably depends on the particular system.
That's true, but we're discussing a very specific system, a Poisson neuron.
No, I mean like in the neural system.
Okay. So for a real neuron is not Poisson, and maybe let's think about that a bit later, and now focus on our model of the Poisson process. For the Poisson process, if I will tell you what is the specific timing of each one of the spikes, would the Fisher information increase? Would you be able to use that to make a better inference of the parameter? No, why not? Yeah, it's really because of this property that the timing of the spikes are completely independent in different times. And the formal way to think about it is that if I would calculate, remember that we started with what is a general definition of Poisson process. It's saying what is the probability for any pattern of times, any list of times. And this list can be of any length. Okay? So for a Poisson process, you take a time interval delta T, and you ask what is the probability of having a certain set of times of spikes that ends up being only a function of n. Okay? Only a function of the number of spikes. Any pattern of spikes with the same number of spikes, whatever that you choose, for any pattern of n spikes, regardless of the time, the probability that that pattern would occur is exactly the same. That makes sense, right? Given the way we think about it as a set of independent result of set of independent events in each infinitesimal time interval. So the timings of these intervals is completely irrelevant to the process. So that means that n is so if now the rate depends only on theta, what this means is that I cannot gain any further information about theta by knowing the timing of the spikes. Okay? I didn't prove it. I just wrote it. But I think it is important for you to think why that's true. It's true because what is this? Let's imagine that we divide our, as I drew it there, actually I don't need to draw it again. We divide our time interval delta t into these infinitesimal time intervals. The number of spikes is just counting how many in how many of them we had a spike, but they're completely independent of each other. So it's quite clear that if 10 spikes have occurred, it's just as likely that they will occur in any set of choices of 10 out of these infinitesimal time intervals. Okay? Does it make sense? Okay. So, using terminology of statistics, we can say that n, the total number of spikes. So in principle, an observation of the Poisson process is to really know what are the times of the spikes. But if you want to infer something about it, about a parameter, about the rate of this process, about lambda, which depends on some parameter theta, the number of spikes is what is called a sufficient statistic. Meaning that we cannot gain any further information about the parameter, about the rate of the process, by knowing, if I tell you what is the number of spikes, that's enough. You don't gain any further information by knowing at what times these spikes occurred. Going back to what we discussed before, this is a very specific feature of the Poisson process. It's really a result of the fact that the spikes at any given interval time are completely independent of each other. For a different model of a point process, this typically will not be the case. Okay? So it could be, for example, that the distribution of times between spikes is such that it carries information. That knowing the timings, if you look at the timings of the spikes and say the difference between the times of subsequent spikes, I can learn something about the parameter that you would not learn by just counting the spikes. For a Poisson process, that's not the case. Okay, let's take a break now.
אתה לא יכול חמישי, ואני לא יכול בשבוע אחרי. חמישי. לא, כאילו, חמישי לא יכול.
I'm not sure I can imagine continuous animation.
כאילו, מבחינתי באמת שיישאר
כן, זאת אומרת, שינוי כאילו,
כן, זה היה פתרון המאוחר. צריך, כאילו, בכל זה שווה לסיים אותו או כאילו, עדיין עם אינפורמציה? לא, אני קיבלתי את השיעור שעבר
Speaking strictly about information, like shared information. But like more classical information as well.
אני עושה גם בזה.
Joint probability factorized with like MRI parallels that I never remember. But basically that if you condition, if you look at the distribution of theta and you condition on T, then if you also condition on X, it stays the same. So it's independent of the observation given the sufficient theory. So the sufficient theory, all you need to know, you know, like knowing the sample that does not add you anything in terms of, if you condition on the sample, the distribution doesn't change. So it's like this. You know the posterior based on, you can calculate the posterior by conditioning only on the sufficient statistics and not on the sample.
לא, אבל כל, אני יוצא מזה הנחה שמי שלא סימן מספר, מי שלא נכנס לסקר, לא אכפת אותו.
It's less clear to me how to solve it.
כלומר, היו עוד הרבה אנשים שציינו שהם לא יכולים להביא, אבל הם כולם כאילו גם לצור שלכם.
כן, אני גם סימנתי שלא, כי ידעתי שאמרתי שאני רוצה להוסיף, ומה הכי נוח לך, שאתה לא יכול. אני לא בטוחה לגבי השאר, אבל זה מה נוח,
אז זהו, אני יודע שאני והחייל קיבלנו סימן אחר. מה זה מה אנחנו? הוא יש לו איזה מבחן לקבל מאוד שמסתמן יומיים יותר, סימן יום לפני.
No, but this is like a subject.
Yeah, but I was just mentioning in the question context, וזה הדרגתי subject, או יכול להיות טיפה מהרביעי עד ה-18?
שבוע אחד אני ועוד איזה כמה ימים. זה הגעתי מה-18.
תגיד בשבוע את הרביעי.
יש לי כמה ניסוחים.
זה יום ראשון.
רציתי לבחור אם יש את זה.
אני אגיד לך משהו שזה יום רביעי ראשי,
יום שלישי?
ביום רביעי הוא אמר משהו שזה הראשון. לא, שבוע לפני זה.
מה פתאום? הכל פה מנורמל, ברור לי שאני בימים שאני לא לומד אף אחד בזמן. לא, לא, אנחנו מחכים שמת. בטח לא שלך, כן. קצת טיפה עכשיו. לא, אני לא רק אקח קנאי
אני מת על השיקול של הכל.
תראה, בואי נשתות שבהם אין דבר כזה. אבל מבחנים תמיד חסר. בכל זאת.
אני חושב בכל המבחנים של העובדים הקטנים ומנורמלים.
מה? מה אתה חושב?
מה, גם בקורס של 20 איש?
אנשים עושים מבחנים ככה, שמבחנים ככה, אנשים שעברו לא יעברו בו.
אפשר לעשות מבחן מושלם, היא פשוט מי שכותב יותר מבחנים לא משקיע מספיק. לא, זה הטענה. אבל אנחנו יודעים שכאילו נורא קשה לעשות מבחן שיעשה את העבודה.
מה זה בושיט? אין דבר כזה.
תשעה? ממתי זה תשעה? מתי זה תשעה?
אבל זה לא אנחנו מפעילים.
אני סטודנט של תואר ראשון, אני לא רגיל שיש לי יותר מ5-6. 5-6 זה כזה, ביקרתי יום חופש באמצע.
אבל הכוונה היא כזאת, במקום שדבר נראה עכשיו,
ואז יתברר לי שכותב הקורס הוא לא אחר מהתיאור. כלומר, זה הקורס שנכתב למישהו שבמשהו מפה. אבל כן, כחוק זה לא היה.
אולי יצא לי מההיגיון שלכם.
אני גם יכול להעיד שכל מבחנים, כל המבחנים שלי, ידעתי שעשיתי במבחן,
לא התכוון.
אם הייתי לא בקורס, מבחן שלי טוב, והגעתי להם.
קורה שם משהו טוב. אני גם, האמת שאני לכאורה לומד בכיתה מהזמונה, ואני לא יודע אפילו.
הבנתי משהו אחד, אני חושב שמה שהבנתי זה מה שהבנתי. מעגלי, אבל
אני מאבד אותם. אני לא מצליח באמת להקשיב על זה 5 דקות מישהו שעושה מתמטיקה רגוע. מה בערך עשיתם עכשיו?
אני דיבר על פרוטוליסטיקו, יש לנו פה פרויקט בייבות, פעם שעברה, אני חושב פה. ניתן ככה לימין, ואז כל מה שהוא אומר באמצע כזה...
זה מתמטיקה שכבר פגשנו.
בעצם זה משהו אחר, אני לא יודע,
done with it, כאילו.
לא, אבל יש...
זה גם נכון, זה גם יש לי איזה
כולנו מתחילים להתכונן למבחן, אבל התפוקה שולית פוחתת כאילו מתחילה אחרי 3 ימים של למידה, לא אחרי שבוע וחצי.
בסדר, אבל לפסיכולוגיה...
בואי נפתח כבר עליתי לי,
לא, אסור להגיד...
אני בפסיכולוגיה היו לי
כן,
פסיכולוגיה
בסדר,
מאוד מבחנים, זה היה סבבה.
אסור להגיד את הדברים האלה בכל הבא. אני כבר יודע, אני למדתי.
כן? בסמסטר הקודם, כן, לא למדתי יום לפני מבחן, אבל בסדר, כאילו, זה לא נכון באמת זה. אבל תראיתי מה עדיף לי, כאילו, בטח מקומות כאלה שהכל, מוסיפן דבר כזה נראות, אז כאילו, זה לא משנה.
לא, אבל אם מחזירו את זה לרביעית, סבבה, לא?
לא, מבחינתי סבבה. אני באמת חושב שלא קשה לי ללמוד את זה, אני דבר יותר.
Okay. Okay, so we discussed the concepts of Poisson process and the Fisher information. If the rate of the Poisson process depends on some parameter. And now let's think about the population of neurons. Of independent Poisson neurons. So imagine that I have n neurons.
Can I ask something?
Yes.
What was the point just to introduce the model in the
Of the Poisson process?
I'm just looking for the point.
Well, the point is that a neuron is a point. We typically think about a neuron as a point process. We measure the timing of the spikes. And therefore, just saying, we count the spikes is a bit too oversimplified. The output of the neuron is just not the number of spikes. The output of the neuron is the spikes. And we think about the context where we observe the spikes over a certain time window, and that's our observation. And as I pointed out, if the model is that the neuron is Poisson, then we actually end up not caring about the precise spiking of the time. But it's important to keep in mind that we can do this because it's Poisson. If the neuron is not Poisson, the timing of the spikes might carry information in addition to the number of spikes. Okay, so population of independent Poisson neurons. So we imagine that. By the way, I wrote here f, and this might be confusing because it's not the same f that only what I meant here is that it's a function of n. We had the 2, and now it's let's not call it. It's not. I didn't mean that it's the same f. Actually, you know what it is? It is the first f. Maybe I don't need to do it because it is the first f. Well, no, f was the mean. F was the mean. So no, f was the mean. So yeah, it's a function. It's a function of n, and we know what it is. It's the Poisson, the e to the minus lambda to the n divided by n factorial. Up to some prefactor because we need to weigh in all the pattern. Anyway, it's really proportional. This is proportional to e to the minus lambda to the n divided by n factorial. Why proportional? Because this is the probability to generate n spikes, and this is the sum over all patterns of timings of the n spikes. So there's a proportionality constant between this and this. Okay, going back to population of independent Poisson neurons. So the firing rate, we imagine that the firing rate of each neuron is some function of theta, And it doesn't have to be the same function for all the neurons. Each neuron might have its own tuning curve. Okay, what is the Fisher information? We know that Fisher information for independent variables is the sum of the Fisher information for each one of them. So the Fisher information is just sum over I going from 1 to n, f prime I of theta squared divided by fi of theta times delta t. For convenience, let me call fi of theta delta t capital Fi of theta, which is what I should have done also initially when I described the Poisson variable. And then I just don't want to carry the delta t over all the time. So this is also sum of Fi prime theta square divided by Fi. Okay, now let's think about a particular example. And this is it's a nice example which is quite important. So the example that I want to discuss so a collection of neurons with what I will call translationally invariant dense receptive fields. I will explain in a moment what I mean by this. Translationally invariant dense receptive fields. So let's imagine that the variable theta is just one-dimensional on a line, and it's actually it can assume values from 0 to L. Okay, so this is theta. These are the values theta. And if I draw the tuning curve of one particular neuron to this variable, let's imagine that it looks something like this. It's some kind of the neuron is tuned to some particular special theta. Neuron I is tuned to some particular special theta which it likes, so it responds when theta is close to theta I, and it does not respond elsewhere, for example. Okay. And now let's imagine that this is really the structure of the tuning curve for all the neurons, except that each neuron has its preferred theta. So this might be theta j. So essentially, my assumption is that Fi, let me use the Fi of theta is some function of theta minus theta I. Okay. And I will assume also that this function has this property that it's the neuron responds in a limited range of theta, that this goes to 0 over a range which is small compared to the range 0 to L. The reason that this is important is that this means that for most values of the parameter theta, really doesn't depend where we are. We always have a collection of neurons that respond to them in the same way, and maybe something will change when we're very close to the boundaries of this region, but if we're not close to the boundaries of this region, wherever we are, we have a particular collection of neurons. Now, the other assumption that I will make is that let's imagine that theta I is equal to I delta theta. So the neurons, the preferred angle of each neuron is just regularly sampling this range 0 to L, and I'll assume that delta theta is small. Compared to what, we'll need to discuss that a bit later, but it's small. So this is the part where so just now I can explain the title. Translationally invariant means that the receptive fields are the same up to a translation. And dense means that the delta theta is small, that we have a neuron responding essentially to we have a dense representation of preferred values of the parameter. So now, what does that mean for the Fisher information? What do you think this means for the Fisher information?
I'm not sure I understood the definition of the theta I.
Each neuron has its own preferred angle, and that's the definition. So
No, but the theta I equals to I.
it's just that we take a set of n neurons, and so delta theta is equal to L divided by n, and so theta I is simply, I L divided by n. So when I goes from 0 to n, or from 1 to n, we sample all the whole range of 0 to n.
Delta theta to be smaller just to include n?
Yeah, so exactly. So for a given L, in order for delta to become small, we need to have many neurons so that we sample densely the parameter, the range. Okay, what can we? Is there something that we can say that will happen in this limit where n is large to the Fisher information using these assumptions? So what does the Fisher information depend on? Well, it depends on the all these f's, but it's in general it's a function of theta, right? Is it a function of theta? No, it will not be. So because of these assumptions, we can expect the Fisher information to be exactly the same. Oh, wait, okay, not exactly, but to become exact in the limit exactly the same regardless of theta. Why? So we have these neurons with these receptive fields which are sampling this range. We have all these receptive fields, and now whatever place we choose for our stimulus, we have a collection of neurons that are responding to it, and therefore we'll get the same Fisher information. Now, in principle, it could be that the Fisher information will be slightly different if our stimulus happens to be precisely on the peak of one of our neurons, or say precisely in the middle between two neurons. But in the limit where delta theta will become small, as we will see mathematically, these differences will go to 0. So in the limit where it's very dense, it will not matter. It's like we have a continuum of preferred orientation for preferred thetas, and therefore it will not matter where exactly we are. And the other thing, so this is the fact that it's dense. The other thing is that because it's translationally invariant, we have the same set of neurons responding, and the only place where things might change is where we're close to the limit, to the bounds. Where here we have the neurons with the preferred orientation thetas here, but we don't have these ones. So we can expect the Fisher information to be different when we're very close to the edges, but we'll ignore that. We assume that L is much larger than the width of the receptive field, and so for most values of theta, we can ignore that. Okay, and what we want to do now is to calculate the Fisher information in this case, and as I pointed out, we expect it to be independent of theta. So let's write it down. So J is equal to a sum over all the neurons. F prime, and at this point I will write it as J of theta still. F prime of theta minus theta I. Oh, and this will be the capital F now, because I just don't want to drag the delta t's all the time. So, F is delta TF. Divided by F of theta minus theta I. Okay, what can I do with this? What can I do with this sum? So we have all these theta i's, which are, the theta i's are densely covering this range, theta 1, theta 2, theta 3. We can replace it, we can approximate it by an integral. So I can say what I'm going to do is I'm going to just divide by delta theta and multiply by delta theta. So far I haven't done anything. But now if delta theta is sufficiently small, this is can be a good approximation to the integral over theta of this function, f prime squared divided by f. So this tells you when is delta theta, when is delta theta sufficiently small for us to think about the neurons as really dense? It's sufficiently small when this is is already a good approximation for the integral. Essentially, it means what it requires is that this function f prime squared over f does not change much over an interval delta theta. Okay. So now this I can say this is approximately the integral. So this is the integral d theta. Let me call it theta wiggle, and the theta wiggle goes for now between 0 and L. F prime of theta, theta minus this theta wiggle divided square divided by f of theta tilde, right? But now I claim that as long as my theta is not close to the edges, then for all the neurons that are actually, then for all the neurons, I can replace this integral by an integral from minus infinity to minus infinity, because all the neurons, this function f, my assumption is that it decays to 0 sufficiently fast that, for example, say the contribution to this theta for this function relative to this neuron, the contribution, if I will extend the integral here to infinity and extend the integral here to minus infinity, my assumption is this function decays to 0 sufficiently fast that that this tail doesn't matter. So this means that I can say that this is approximately equal to 1 over delta theta, an integral d theta tilde f prime of theta minus theta tilde squared divided by f of theta minus theta tilde, now from minus infinity to infinity.
What about the bound? You just take
Well, the neurons that are close to the bound, in any case, they're not responding here. So this function is 0 for them, as long as I'm not close to them. So it's like this is like I'm adding more neurons. Also, I'm adding more Actually, we should think about it. I think let's think about it a bit more carefully. So this is theta, and I'm adding contributions from all these functions. And I'm just saying, actually, I should have. I think I said it incorrectly. I'm adding contributions from all these functions, and it's as if I'm adding an infinite number of neurons in this side and an infinite number of neurons in this side, right? And as long as I'm far from the edges, these neurons that I'm adding are adding nothing. Their contribution is negligible, assuming that this function f decays to 0 sufficiently fast. Okay, so it's as if instead of thinking about it as a population with values of theta starting from theta to L, I'm thinking about it as if it's infinite. This is actually what I've done here. Okay, so now you see that once I've done that, theta doesn't matter because I can do a change of variables and call theta minus theta tilde my my new variable. Okay.
Sorry, what I wanted to check now.
Okay.
But when theta I is, what you said is relevant if theta I is somewhere in the middle of this.
No, well, theta, the sum is over the theta. The theta is fixed, and I'm summing over the contributions from all the neurons.
Yeah, but if it's...
And I'm assuming that my neuron is not very close to the bounds.
But when it is, then what?
Then it will change. The feature information will be different. But the range of over what range relative to the bound will it be different? When I'm close to the bound, up to about the width of this receptive field. So I assume that the length is much larger than the width of the receptive field, and I'm just thinking about the thetas which are not as close to the bound within that range. Okay, so once we've done that, we have here the difference between theta and theta tilde. I just can call this a new theta tilde tilde. Okay, so this will be the same as here. Maybe theta tilde tilde is too many tildes, so we can do theta prime. So this is equal to 1 over delta theta integral from minus infinity to infinity. Actually, what I'm going to do is define theta prime is theta minus theta tilde. And when I do this change of variables, so here I will write theta prime, here I will write theta prime. Here I have a minus sign, but I also need to flip the range of the, when theta tilde is equal to infinity, theta prime is minus infinity. So if I flip it back, I cancel the minus sign. So I'll get here an integral d theta prime, f prime of theta prime. I see why f prime is not good. Let's do f bar. Sorry, f prime and theta bar. It's a bit confusing otherwise.
Why did you not say the capital?
Oh, and it's the capital, yes. Thank you. F bar prime of theta. Sorry, f prime of theta bar squared divided by f of theta. Okay, and that's what we got. That's what we have. Now remember.
Theta bar.
Yes. Okay. This is some function. This is just an integral. It's a function that depends on the function f. So if the function f looks like this, you need to take its square, divide it by itself, do the integral from minus infinity. It's some number, right? Now delta theta, what is it? Delta theta is L over n. So 1 over delta theta is n over L times this integral. And so you see that if we make the neurons more and more dense, add more and more neurons, the feature information becomes proportional to the number of neurons. Now there's another thing that happens when we add more neurons, which is that our whole approximation becomes more correct, because really our ability to replace the discrete sum by an integral depended on the fact that the receptive fields are dense, right? So as we increase the number of neurons, just the approximation becomes more and more correct, but also we have a factor of n because we have more neurons, we have more independent observations. We could have done things a little bit differently, and we could decide that as we add more and more neurons, we scale the firing rate of each one of them so as 1 over n. Okay? If we would do that, then so if this f we would take it to be proportional to 1 over n, then here we'll have 1 over n squared divided by 1 over 1 over n. So overall we'll get 1 over n multiplied by n, and the n will cancel. So you can think about this limit where you throw in more and more neurons but make their firing rates smaller proportionally to that. In that case, in the limit where they're very dense, the feature information will just approach a certain number. Okay? Okay. Yes?
We know that the integral doesn't ever
Well, that's a good question. It depends on how this function decays to 0. So it will not diverge if this function decays to 0 sufficiently smoothly and fast. Okay? And otherwise, it might diverge.
Can you see the last part of the 1 over y? The number before, right?
Which point?
You said that
About the number of neurons? If, okay, so maybe I'll write it down. Note, if we take the limit in such a way, we set f to be f of theta to be proportional to theta to 1 over n. So let's suppose that we take it to be some function of theta divided by n. So as we're adding more and more neurons, we're making the firing rate of each neuron smaller. In that case, we will get that J will approach some, J will be independent of, becomes independent of n in the limit n going to infinity. And the only reason in this case, the only reason it's dependent on n is the fact that only in the limit of n going to infinity, the approximation that we did becomes precise. So as long as n is finite, as I mentioned earlier, as long as n is finite, the Fisher information actually is not just independent of theta. It's slightly different if we're here relative to here. It's exactly the same if theta is here or here or here, up to the neglect of the boundaries. It will be very similar, it will be the same here and here and here, but it might be slightly different here and here and, you know, if you're at the where we are relative to this difference between the receptive fields of neurons. The limit where they're very dense, this effect goes to 0. Okay. So now I want to discuss a certain application of this result. And what I want to ask is whether it's good to have narrow or wide receptive fields. So, okay, so let's imagine that we're allowed to choose the structure of this receptive field. Let's imagine that it's a Gaussian, but we're allowed to decide on the width of the receptive field. We can make the neurons with wider or narrow receptive fields, but we always make sure that we're in the range where these assumptions are true, that it's translationally invariant. So the range, so the width will be small compared to L, and also and it will be dense. So is it good to make the receptive field wider or narrower? What do you think? What if we think about the single neuron? Is it better to have, in terms of Fisher information, a wider or a narrower receptive field? Why? Yeah.
Then if you are deviating further,
Okay.
some response from this.
Okay, but on the other hand, if we're close to the, as long as we're close to the, within the range in which the neuron responds, if the receptive field is narrower, the derivative is sharper. So it's more, the response of the neuron is more sensitive to the parameter. And we see that in the expression for the Fisher information. If the derivative is larger, that increases the Fisher information. So there's a certain trade-off here, right? Which is not, it's not obvious how it will play out. If we make the receptive field more wide, on one hand, some of the neurons will be more weakly responsive to the stimulus, their Fisher information will go down, but on the other hand, we'll have a larger number of neurons that are going to respond, right? Okay, so we need to... But the Fisher, I'm talking about the Fisher information for each one of them. For some of them, it will increase because they will, the derivative with respect to the parameter will be larger. But on the other hand, if we make it narrower. On the other hand, if we make it narrow, some of the neurons will just be non-responsive anymore. So that there will fall. There will be a smaller number of neurons that respond to the stimulus.
But if n is large, then
No, even if n is large, if the stimulus is here, then the number of neurons that are responsive is proportional to the width of the receptive field, right? Right now, if I make all these tuning curves narrower by a factor of 2, then the number of neurons that will respond, that will be within the range of this theta, will be smaller by a factor of 2, right? So we need to check what's going to happen, and here's how we can do this. So we're going to work with this expression. Sorry, not this expression, this expression.
To try to fit what sense? Try to fit sense of how information.
That there are two. When we just try to think about it conceptually, we see that there are two things that happen which have opposite effects as we make the tuning curve more narrow. On one hand, some of the neurons are more sensitive to the parameter, and therefore their feature information is increasing. On the other hand, fewer neurons are responding, so there are also neurons whose feature information is decreasing.
Yeah, but my question is, what is the effect that we can?
So we want to ask whether overall making the tuning curve narrower will improve or will increase or decrease the feature information. That's what we want. Of the whole population. Of the whole population. Right? So the way we're going to think about it is, let's just assume that f of theta is some function of theta divided by some parameter s. And we're now allowed to play with this s. So if I would plot f of theta as a function of theta, maybe this would represent a case where s is large. And when s is small, I get a narrower, the same shape but a narrower tuning curve. Right? Because when s is large, I need to vary theta by a larger amount to make the same change in the argument of g. So the tuning curve will become wider. And now I just want to plug this in this expression and see whether increasing s or decreasing s is how varying s affects the feature information. So let's just do this. J is equal to n over L integral d theta bar g prime of theta over, I don't need now the theta bar anymore. Let's just call it theta. G prime of theta over s square divided by g of theta over s, from minus infinity on to infinity. So let's just define a variable x, which is theta over s. So dx is 1 over s d theta. X still goes from minus infinity to infinity. Now, Now, the derivative here, we have to be a bit careful about what we mean here. Actually, you should have stopped me and said that what I'm writing here is wrong. Because what I should write here is a derivative of f with respect to theta. So df to the theta, let's do it df here. df to the theta is equal to 1 over f dg to its the derivative of g when we plug it in its parameter, right? G prime of theta over f. And therefore here, what I wrote is wrong. What I should have written is 1 over f g prime of theta over f. And now also we have that d theta is equal to s dx. So this is equal, so I have here 1 over s squared. I have another s coming from the fact that d theta is theta dx. So I can write that this is equal to n over L times 1 over f times an integral dx g prime of x squared divided by g of x. Okay, so again, we had 1 over s squared coming from here, and a single s coming from here, and overall we have 1 over s.
Why do the integration factor change?
Because minus infinity, when theta goes from minus infinity to infinity, x also goes from minus infinity to infinity, right? So this is some number. So what do we get? What did we get? What is the conclusion? That it's better to make s small, right? The Fisher information becomes large when s is small.
But is it the same number?
Well, I don't care. This s is no longer in this expression. This is just some integral. So now, you see that it's beneficial to make s small, meaning that we want to make the tuning curves as narrow as possible. Now, is this true up to, we just want to make them infinitely narrow? What will happen if we make them more and more narrow?
There's a different kind of relationship between n and s, I guess, because if they're very narrow.
Right. So as long as I'm saying I want to have n neurons, remember that we had our assumption that the tuning curves are dense. Right? So for a given n, there's a limit to how small I can make s such that that assumption is still correct. At some point, if this is my range 0 to L, and I have receptive fields here, if I make the receptive fields very narrow, then the assumption of dense receptive field is not going to be correct. So all this calculation will break down. So essentially what happens is that you want to make the receptive fields narrow over a width which is comparable to the difference between adjacent the preferred values of theta for adjacent neurons.
Sorry, what is considered dense enough? What is
So when will the assumption of dense break down? It will break down more or less when the receptive field becomes comparable to the difference between the width of the receptive field becomes comparable to the difference between the preferred thetas of subsequent neurons. So as long as we have something like this, the assumption of dense receptive field is still reasonable. But if we would try to make the receptive field even smaller, then this whole calculation would break down. So what we learn from this, nevertheless, is that if we have many neurons with receptive fields equally distributed on the line, we want to make the receptive fields narrow. Up to some point. Now, one thing to, okay, so now what I want to do next is to discuss what happens if the variable is not one-dimensional, but say two-dimensional or three-dimensional, okay?